This lecture will tell you all about the PCR reaction and some considerations in doing the reaction. First, I would like to remind you about polymerases. There are several different ways that a polymerase can add bases to a growing DNA chain. A polymerase can be a processive enzyme, and a processive enzyme is going to add multiple bases to the growing 3' end while still staying bound to the DNA. In contrast, a distributive enzyme adds a single base, releases the DNA, then in another round would grab onto the DNA again and add another base. So generally, processive enzymes are much faster, can add far more bases per unit time than a distributive enzyme because it's just more streamlined. To remind you of the reaction that's happening, you have the template strand and you have the primer in a 5' to 3' direction, and the polymerase is going to add a complementary base to the template strand, and the polymerase will incorporate the DNTP and release the pyrophosphate. In the PCR reaction, we have the original sequence that is to be multiplied, along with primers and DNTPs. The first step that happens is a denaturation step. This generally happens at around 94 to 96 degrees. When you heat the DNA to that temperature, generally it's breaking all the hydrogen bonds and the two strands of DNA separate. Then the temperature is lowered to an annealing temperature. Now, an annealing temperature can vary quite a bit, and it's going to depend on the GC content of the primer as well as the length of the primer. The longer the primer is, the lower the annealing temperature generally is, the higher the GC content, because G's and C's form 3 hydrogen bonds versus T's and A's only forming 2 hydrogen bonds. So the higher the GC content, the better the primer is going to stick to the DNA. So again, the lower the annealing temperature. The annealing temperature is generally set by the sequence, as I just said. So when you order an oligonucleotide from a company, they will give you a printout, usually based on your sequence, and tell you what your melting temperature is, your TM. And the melting temperature is what temperature do I need to raise my DNA to release the primer from the DNA. And so you want your annealing temperature to be approximately 5 degrees below your melting temperature. After the annealing step has gone forward, the polymerase, in the presence of DNTPs, is then able to extend those primers in a 5' to 3' direction. And this is called an elongation step, and polymerase generally, that's used in PCR, the polymerase generally works best at 72 degrees. Original DNA polymerases that were used in this type of a reaction, not in PCR, but this type of a reaction, worked best at 37 degrees. And the downside was that the temperature needed to denature the DNA for the next round of replication generally inactivated the polymerase, meaning more polymerase had to be added each round of replication. One of the things that Kary Mullis did in getting the Nobel Prize for working on this process was realizing that Thermus aquaticus, which had been isolated from hot springs in Yellowstone, and actually worked best at a much higher temperature, works best at 72 degrees, and can withstand being heated to 94 to 96 degrees for a while without losing activity. So he realized that this could be used with primers and the template DNA and put together in this whole process. So he did not invent Taq polymerase by himself. He did not invent oligonucleotides, but what he did is he drew all of these things together in this very important process. So after this elongation step has been done, you're ready for another round of replication. So then you go to back, each of these goes through a denaturation, an annealing, and elongation again. So you start with 1, you have 2, then you have 4, etc. By the time you're finished with 30 rounds of replication, you can begin with 1 copy of the DNA and have over 1 million copies of your target sequence. I would like to point out, when doing PCR, the entire length of the DNA is not amplified overall. So if this is a long stretch of DNA, and this is where our primers are binding within that long stretch of DNA, you end up just amplifying the portion of DNA between those 2 primers. So how does this happen? Well, this primer is going to extend along a 5' to 3' direction, depending on the length of the DNA, maybe not all the way to the end, but we're drawing it to the end just for illustrative purposes. And this other primer is also going to, go a ways past where the first primer bound, maybe to the end of the DNA, depending on the size. So then you will go through a denature and anneal step again. So here we have our original length and our original length, and here's our 2 new strands of DNA that were synthesized. And so notice that this primer that bound here is still binding here. The primer that bound here is still binding here. And now we're starting to see when this one amplifies and that one amplifies, now and they elongate, now we're starting to see our target size of DNA. So again, now we have multiple strands. We've doubled our number of strands again, and we're denaturing, and we're annealing, and we're going through another extension step. So now we're starting to see just our target sized fragments in here. So even though every single round of replication, because the original strands are still there, every round of replication you're going to arithmetically have strands that are longer, you're going to logarithmically amplify your target sized fragments. So after our 4th round of replication, now you can see many, many more of our target sized fragments compared to those longer original strands. So you can see that by the time you have gone through 30 rounds of replication, the few longer odd sized strands that are there are not even going to show up on a gel. And so what you're going to see on the gel is basically all of these target sized fragments. In our PCR reaction, you generally have a buffer, and you have a certain amount of magnesium chloride. Now remember that we've said that divalent cations are necessary for enzymatic activity. They're necessary for proteases sometimes, they're necessary for DNases, but they're also necessary for polymerases. And polymerases use magnesium chloride because the magnesium chloride actually forms a structure with the DNTPs. So the nucleotide triphosphates are negatively charged, and they sort of wrap themselves around the the positively charged magnesium, and they form a particular shape. And it's this particular shape that's actually recognized by the polymerase. So if you don't have any magnesium chloride at all in your solution, then your DNTPs will not be forming that characteristic shape, and the polymerase will not be recognizing that shape, and therefore the polymerase will not be adding any of those DNTPs onto the 3' end of your growing chain. So, as I said, in the reaction, you have buffer, magnesium chloride, DNTPs, and we've already talked about how the primers and the template DNA are working in the reaction. You want to make sure that you have autoclaved water. You don't want to start off with any foreign DNA or bacteria or anything like that growing in your water. So generally you want to make sure that you're using very, very clean water in your reaction. And then you have the TAC polymerase, the Thermus aquaticus polymerase. One consideration when putting the reaction together, if you simply try to put everything together at room temperature, what can happen is you can have something called mispriming. And mispriming is where you have a primer that has some complementarity to a sequence other than the target sequence. So if this is the target sequence where it's meant to bind, but there's some complementarity down here where it can mistakenly bind, then you're going to get incorrect sizes of your amplified DNA. You need to be able to reduce mispriming. You don't want this to happen. And it's kind of inconvenient to try to assemble reactions at over the annealing temperature. It's very difficult to sit in a 95-degree room, for example, where your DNA is going to be denatured, so your primers are not going to be binding to incorrect places on the DNA, for example, or even sitting in a room at your melting temperature, which maybe is 73 degrees Celsius. That's a pretty darn difficult room to spend much time in at all. So rather than trying to do something like that to assemble your reactions, we have some chemical shortcuts used to help out the process. One of the things that has been done in the past is adding DMSO, dimethyl sulfoxide, to the reaction. And DMSO destabilizes the hydrogen bonds. It destabilizes all the hydrogen bonds. So if you have something that's going to be sitting down on an incorrect location on the DNA, because there's partial hydrogen bonds, but maybe not as good as its original target sequence, for example, then it's going to reduce that number of hydrogen bonds, meaning that, sure, the hydrogen bonds between the primer and the target sequence are also reduced, but there are enough that it's still going to stick even in the presence of DMSO. So a partial match is less likely to bind, and something that's a perfect match still retains enough hydrogen bonding to be able to bind. But this does lower the annealing temperature, and so you'd have to take that into account. Another process is doing something called hot start. And in hot start, you are basically trying to make sure that everything that the reaction needs to take place is not together in one tube until after the annealing temperature is reached. Now, one way of doing this is manual addition of the polymerase, for example, or some missing ingredient. And if you're only doing a single tube, sure, you can do manual addition. But more and more often, as people started doing 10 tubes at one time or 20 tubes at one time, manual addition became a little bit unwieldy, trying to make sure that you had enough time to, for example, add polymerase to all 20 tubes in the 1-minute denaturation step. So it got to be kind of difficult. So then people went to using wax beads, physically separating the components with a wax bead. So what they would do is they would mix some of the things in the reaction, the buffer, the magnesium chloride, the primer, the template, etc. They would leave out maybe the DNTPs and the polymerase. So they would have the aqueous solution in the bottom, and they would have a little wax bead, and they would heat up that wax bead so that the wax would melt and form a positive seal on top of these items. And then in the other half of the reaction, they would add DNTPs and polymerase, maybe some more aqueous solution. So there was a physical separation preventing them from coming together. And then when you put them into the PCR machine, as you're heating up the PCR machine, once you pass the annealing temperature, the wax then is going to melt. And when the wax melts, this solution comes crashing down into this solution right here, and now they're all mixed, and it's over the annealing temperature. And that worked well for quite a while too, but it took a little bit of extra time to be able to set that up. So then one company came up with a great idea. They blocked the polymerase active site with an antibody. So now they can just put everything all in the same tube, don't need a wax bead or anything like that. The polymerase active site is blocked with an antibody, so the antibody does not let the polymerase add anything until you are basically over the annealing temperature for the first time. Now this means that you can go ahead and set it up at room temperature, and sure, you're going to have a bunch of mispriming events with primers when you first set it up. But the polymerase is not going to be adding bases onto those misprimed areas. Then you increase the temperature, and as you increase the temperature, those primers that sit down on the DNA in incorrect locations are now coming off of the DNA, and then you have the denaturation step. At this point, you have a high enough temperature that you're denaturing that little antibody that's blocking the active site, and then when you decrease the temperature to the annealing temperature, it's generally a high enough temperature, 5 degrees below the melting temperature, so that the primers are sitting down on their correct locations, and you don't have primers binding to incorrect locations nearly as often. So this is an example. If you used a regular Taq polymerase, you can see a whole bunch here of incorrect locations that have been bound and started by having polymerase that was not blocked. But if you have a polymerase that is a hot start, you can see now you're only getting the one correct size that you are expecting. After your PCR is completed, you're going to run it on a gel. And depending on what size you are expecting, you may run it on a polyacrylamide or you may run it on an agarose gel. A polyacrylamide gel is generally able to separate between 10 to 800 nucleotides or base pairs. An agarose gel is able to separate 300 to 50,000 nucleotides or base pairs. And it can do this by changing the percentage. There is no 1% of acrylamide or agarose that's going to work for the entire size range if you need to get good separation. But if you're trying to separate, for example, 50,000 from 30,000 base pairs, well, then maybe you would want to use a lower percentage of acrylamide. Or if you were trying to separate 300 from 500 base pairs, you would probably tend to use a higher percentage of acrylamide. So agarose, agarose, 300 to 400 would be using agarose. So agarose percentages range from 0.8% to 3%, for example. Polyacrylamide gels range from 4% to 20% and will will ideally separate different ends of this range at those two different percentages. Things which might be used to separate in a polyacrylamide gel are small RNAs or small DNA restriction fragments, for example. On the other hand, agarose, you would separate the larger RNAs or the large DNA restriction fragments in an agarose gel because maybe they're over the 800 nucleotides or base pairs, so you would want to use agarose as a better size range. Now, between those two gels, there's different types of buffering systems. You can have normal salt buffers, tris borate or tris acetate system, and tris borate tends to be used in polyacrylamide, tris acetate tends to be used in agarose gels. But maybe you want your DNA to separate only by size. So if, for example, you have an RNA molecule, and it's important that you know the length of your RNA molecule, not the three-dimensional structure of that RNA. You want it to separate only by length. Well, then you would use a denaturing gel. If you were using an acrylamide gel to make it denaturing, you add 7 molar urea to it. Urea is a chaotropic agent, induces chaos, and basically the urea again destabilizes all of the hydrogen bonding so that the DNA is running completely linearly, or the RNA is running completely linearly and separates only by size. Running a denaturing agarose gel is a little bit more difficult. If you are running DNA on an agarose gel, you can use sodium hydroxide to denature your DNA, but you cannot use sodium hydroxide with RNA because of the structure of it. Sodium hydroxide will break apart the ribose ring on the RNA, so you have to use other methods, none of which are good. So when you are doing RNA, you can use methylmercury, extremely toxic. Methylmercury will go through normal latex gloves, for example. People have died from not using proper precautions from methylmercury. So sure, it'll denature your RNA, but is the toxicity worthwhile? And I think generally it is not. You can use glyoxal. And glyoxal is a good option, but some people are very, very allergic to it. And sometimes you don't know that you're allergic to it until the first time you use it. So then you get these huge, welty bumps, all over your skin from being exposed. You get hives, basically, from being exposed to the glyoxal. Formaldehyde is very easy to use, but it is a carcinogen and it is regulated. You basically have to keep track of all the amounts of formaldehyde, make sure that you are properly disposing of it in special containers and things like that. So there is no perfect solution for RNA. There's just different degrees of bad, basically, when you are trying to do a denaturing gel with agarose. And when you are running this gel, this is an example of different sized pieces being run, for example, on a 1% agarose gel. So you can see that even though you have some different sized fragments on this agarose gel, you can see that some portions of it separate linearly, while the two extreme ends don't tend to separate linearly. So what you can do is, if you need to separate something in this range, a lower molecular weight, this is where you would have to increase the percentage of your gel. And again, this holds true for whether you're doing agarose or polyacrylamide. A high percentage gel is going to separate the lower molecular weight better, and a lower percentage gel is going to separate the higher molecular weight better. So if you were to take these same fragments and try to separate them on a 3% gel, now these would be linear in this range and be separating very well, but you probably wouldn't be able to separate anything 2,000 to 3,000, they'd probably run almost identically. And 6,000, 12,000, 19, and 29 would definitely all be, lumped up in one portion near the top of the gel. But if you needed to separate these a little bit better, you would do a lower percentage of a gel because those separate the higher molecular weights. So if you did a 0.8% gel, for example, now you'd be able to separate the 29 from the 19 from the 12, but, the 2000, the 200 through the 2000, these would not be separating as well. So these are all considerations when carrying out a PCR and running the gel.